Questions before we start? No? Okay, so again, as I mentioned, I would like to do a couple more examples. So, but you already have the knowledge of partial fraction. So let me give you one for you to try, and I will take attendance, because otherwise I'm not gonna take attendance again today. So evaluate and try this one. And basically this is here to let you know that it doesn't mean that you need to have a rational function right away. Sometimes you may have to do some stuff first. For example, what should you do here before anything else?
Factor out the.
So this is not a rational function. Do you realize this? A rational function has to have polynomials on top and bottom. It's a quotient of polynomials. These are not polynomials. Trig functions here. So what should we do first?
I'm going to say get rid of the trig functions, but I don't know how to do that. So don't ask.
Yes, you know how to do that. How do you do it?
Is it with trig substitution?
No.
Can we make a triangle and replace that cosine with that?
No. Don't. Okay. This is another thing. Don't make your life difficult.
Right.
You are learning a lot of techniques, but then you are going to be tempted to use the advanced techniques for very easy problems. Don't do that. Always start from the easy stuff first. U sub, right?
So like sine squared x is u squared and 3 sine x.
So what is your u sub? U equals?
Sine x.
U equals sine, right? And your u is right there, cosine. It's right in the top. And then you turn this into a rational function of u. And then you activate the partial fraction and whatever you need to do. Yes? So remember, you have a lot of techniques now. So whenever you encounter an integral, you need to run through through all your techniques, but from the easier ones down to the most complex one, because the integral could be pretty easy, and then you want to, use a very complicated technique for that one. So here the hint is, so the idea is let u be equal to sine, because then du is cosine. And so you're gonna have 5 over u squared plus 3u minus 4 du. Yes? So now do this one. Let me take attendance as you work on this. All right, so remember, those of you that are online, when I call out your name, type here in the chat. Carl Abbey. Okay, Gisela Costa.
Everyone's waiting for the end, so you're getting all the people that just logged in and check out.
Yeah, there are, that's what concerns me. Yeah.
They'll be back at the end.
No.
Say, oh, I was
Helen, okay. Elena Bistri. I always have a hard time. Okay, here. I'm not sure if I say it correctly, your first name. Corina Cardenas. Okay. Jason Carver. Ángel Concepción. Okay. Joel Correa. Andy Diaz. Okay, Joel Correa is here. Andy is here. Melanie Gavilanes. Wilson Lee Jeffra. Daniel Herrera. Adam Hirschon.
Yeah.
Franklin Yanes. Gina McKean. Joshua Miller. Paul Monroe. Orangel Olmos. Robert Sarabia. Kyle Silvera. Laura Sayas. Okay. All right, so we have some time. So now let's go ahead and let's do this. So what should be the, first of all, any questions on the substitution? Do you understand why we did that? Just to turn it into a rational function, okay? And the purpose is so we can do partial fractions because now we know how to deal with this. Okay, what do? We factor out the denominator. So in this case, it becomes, so what is it? U plus 4. Okay, it shows the wrong letter because my U's and my 4's, they look too similar. So you understand which one is the U and which one is the 4, right?
One on the right is the U, right?
No. Let me try to do, no, that's even worse. It looks like a W. Okay. U plus 4, U minus 1. Okay. All right. Okay, so du. So now, once we have factor, what do? So we do the splitting, right? So it's time to leave the integral alone for a second, and then now let's do some algebra. So U plus 4, U minus 1. Okay, so tell me, what's splitting?
A over U plus 4.
Okay.
Plus B over U minus 1.
Very good. So remember, for each linear factor, you play this game. Then if you have quadratics, you do the same thing, but with a degree 1 on top. Okay, ax plus b or whatever. And if you have some powers, you will get that many fractions for that factor. You need to increase the power 1 by 1, etc. Okay, good. All right. So then here, what do we do next?
You multiply both sides by what's under 5.
So we clear denominators, right? So we multiply by u plus 4, u minus 1, the whole thing. So on the left, we're going to get a 5. Now, on the right, what do we get?
A parentheses U minus 1.
A parentheses U minus 1, good.
B parentheses plus B parentheses U plus 4.
Okay. Are we good? Does the shortcut works here? It's going to work very nice, right? No need to do systems. Okay, so what do we set for U?
1 and -4.
Okay, so let's see. Which one do we do first?
1.
So let U be equal to 1. Then what equation do I get as a result?
5 equals 5B. Yeah.
5B. Good. Everybody following this? So what is B? B equals 1. Then, now that we know B, let's find A. What do we need to do? -4. Good. What equation do we get as a result?
5 equals -5A.
So -5A. So what is A? -1. And you know, if you have time to spare, you can always, when you put the composition, you can always add the two things and check to make sure that, you know, the constant that you found actually work and give you the function, okay? So you can check. All right, so so that means that this here is equals to put this in the wrong place. So what I did was I multiplied by u plus 4, u minus 1. So what we found is that this equals to negative 1 over u plus 4 plus 1 over u minus 1. Yes? All right. So now we come back and we finish our integral. So this is equal to the integral of, so I'm going to put the decomposition. I'm going to flip. I'm going to write the last one minus the first one. Okay. So 1 over u minus 1 minus 1 over u plus 4 du. And what type of integrals are these? Ln. So this is ln of absolute value of u minus 1 minus ln of absolute value of u plus 4 plus c. And now remember, our variable is not u, our variable is x. Therefore, we need to put back. So what was u equal to? Sine. So this becomes ln of absolute value of sine minus 1 minus ln absolute value of sine plus 4. And if you want, you can combine these two ln's and put as a quotient, but I'm just going to leave it like that. Okay? All right. Questions?
Just to be clear, if we were to combine it, it would be sine, ln of sine of x minus 1 over sine of x plus 4.
Yes.
And then
The absolute value. The absolute value has to stay there. Yeah. If you want to get rid of the absolute value, for example, I claim that I don't really need the second absolute value. Do you see why?
that always has to be positive.
Why?
Because it's sine of x plus 4 is plus 4. It means I would be above the 0 at all times. If I'm
Okay, good.
it correctly.
Okay, good. Yes.
Okay.
Okay, good, because this point is about 0. Now, I was just going to say, because sine is between 1 and negative 1, right? So the lowest it can go is negative 1. If you do plus 4, the lowest it's going to go is to 3. So this is exactly what you're saying. So we don't really need the absolute value here. And do we need it here? Yes, we do, right? Now, you could argue that, okay, absolute value of sine minus 1 is the same thing as whenever you have something inside an absolute value, you can flip it. Because a minus b and b minus a, they just differ by a sign. A minus b equals minus b minus a, right? But when you do absolute value, that minus doesn't matter. So what I'm saying is, when you have something inside an absolute value, you can just flip it, and equality holds. Okay? Because a minus b and b minus a, they are negative of each other. Do you understand this? But the absolute value kills the negative. So if you wanted to get rid of the second absolute value, you can do it. You just need to flip this and write 1 minus sine instead. And then that will always be positive, because when sine is positive, it's no more than 1. So 1 minus that is going to be, and when sine is negative, then you have a minus in front making it positive, so it will be positive. So you could do that. But I'm just going to leave it like that. Okay? All right, so what I'm saying is you can write this answer without the absolute values. Questions for this one? No? Okay, let's do another one in which factoring may be. So I want you to understand that the hardest step in here in general is the factoring step, because the rest is pretty automatic. The solving a system of equations is, is pure algebra. There's really not much going on there. The hard step is the factoring step. It's just that, usually you are given nice problems in which the factoring is actually the easier part, if you will, like in the previous problem. But in general, you need to understand that factoring is what can get you stuck for some time. For example, let's take a look at this one. What do? So first we look at it, we realize, so let's see, we have some stuff going on in the chat. I didn't see the chat. Forget, okay. Okay. So we have to look at it as a rational function, so you should be thinking, first of all, take a look and see if there is a quick and easy substitution that we can make.
We can make the denominator du, and the top can be du. We just have to multiply all by 3.
Very good. If we multiply this by 3, then we're going to get exactly the derivative of the bottom. Yes? And then this would be a super easy integral. Okay, that's not what I wanted to do.
You want us to struggle with
I wanted to factor this, just to show you how to factor this.
Okay.
Right? Because what if you didn't have, let's say if instead of a 1, we had something else going on here, what do? Right? So that's what I wanted to do. But fair enough. This turns out to be easier than. Anyways, let's do the easy part. And then I just explain the factoring and then that's it. Because I want you to see an example, or at least to see me, to remind you of factoring stuff like this. You learn this back in calculus. Okay? But for example, if you had this, if it was +2 instead of +1, you have to go through the factoring that now I'm going to explain, etc. It just turns out that we're so lucky that the derivative of the bottom, here's what's going on. If we let u be x cubed plus 3x minus 4, then du is 3x squared plus 3. Yes? And actually, and then, we can take out a 3 from here. Just gonna do it like this because we're used to this already, and divide by 3. And so du over 3 is basically our numerator. Do you understand this? So this integral becomes 1 over u times du over 3. So this is 1 over 3 ln absolute value of u. So that's just 1 over 3 ln of x cubed plus 3x minus 4. And we are done. We'll walk away.
So can we redo it with the 2 instead of a 1?
Yes, of course we can. The problem is that if I put a 2 there, it could be that the system that we end up having is nasty and messy.
Right.
You see, it may not be a nice problem. We're going to spend here like 15 minutes. I would rather do something else. But yeah, I mean, really the complication is being able to factor this. The rest is just figures. It's solving the system of equations and so on. I mean, I can try, but if it gets messy, I will just stop. Okay? Because I don't want to use too much time on that. But okay, so that's this one. Let's call it B. Let's do it with the, actually, even, what if it was like this? Okay, so I mean, we can put +2 and so on, but what if it was just like that, for example? Right. This guy. All right, so my point here is that I'm gonna try to do. So we need to do here partial fraction, but before doing that, step number 1 is factor that denominator. So now this is a degree 3. This is not a degree 2 polynomial. So we know that we're expecting at most 3 zeros, right? But you need to understand that some of them could be complex, or maybe all of them are real. Okay? We know that there is at least one real solution, one real zero. Do you understand this? A polynomial of odd degree has at least one real zero. Why is this? Think about the end behavior. Because the degree is odd, that means that one side is going to go to negative infinity, and the other side goes to positive infinity as you go to the right or to the left on the x-axis. Yes? Remember, odd degree polynomials, they either look like this, the end behavior resembles this power function or this power function. It depends whether your leading coefficient is positive or negative. This one is with a positive leading coefficient, and this one is with a negative leading coefficient. Like an x cubed, an x to the 5, x to the 7, etc. Any power function with odd degree, they look like this. And polynomials, the end behavior is the same as the end behavior of its leading term. Okay? So when the degree is odd, that means that one side is negative and the other side is going to be positive. It's continuous, it has to cross the x-axis. So you're going to have at least one zero. When the degree is even, it's different because, they look like this or like this. So it could be that it's happening above the x-axis all the time, going up, and it never touches, so all your zeros are complex. That's the hardest case, because now you don't have any real zero to look for, okay? But in this case, we know that there is at least one zero, one real zero, so let's try to find it. And the good news is that once you find one zero of a cubic, then you're basically done, because then we do division, okay? And once you do division, you can factor this as a linear times a quadratic, and once you hit a quadratic, you have quadratic formula. So with a quadratic formula, you can find the zeros, regardless of what they are. So here we just need to work for one zero. And of course, this is not a precalculus class, so we're not going to do the most complicated case. And so this one is pretty simple. Can you tell me what would be 1, 0 here? Try again. 1. So here is the quick hint. When you see a polynomial and you're looking for zeros, and you're wondering whether 1 is a 0 or not, just go ahead and add the coefficients. If you get 0, then 1 is a 0. Because what do you do when you plug in 1? You're basically adding the coefficients of your polynomial, right? You see, 1 plus 3 is 4, minus 4 is 0. So I know 1 is a 0 of this guy. Yes? In general, what you should do is a rational zeros theorem. Let me remind you of this, just in case. So, rational zeros theorem. Basically, rational zeros theorem says that if the function is going to have, if the polynomial is going to have a rational zero, it will come from the following list. So the zero is going to be of the form a over b, in which the factors of a, so if a over b is a 0, then the candidates for a, they come as factors of 4, the constant term, and the candidates for b, they come as factors of the leading coefficient. What's the leading coefficient? This case is 1. So that means the factors of 4 are plus or minus 1, plus or minus 2, plus or minus 4, and the factors of 1 are just plus or minus 1. So all possible rational zeros, if there is a rational zero, it's going to be from this list, and then you just make fractions where the numbers, the factors of a is what goes on top, the factors of b is what goes in the bottom. So what's the, yes?
For the theorem for like all, to find any rational zero, it's a would be 1, 2, or 4.
I'm going to write the full list now.
Okay.
You ask me now. So the first thing that you do is find the factors of the constant term. Then find the factors of the leading coefficient. Okay? And then you start making fractions from the top list, of combination from the top list with the bottom list. So it would be plus or minus 1 over 1, that's just 1. Then 2 over 1, that's just 2. And then 4 over 1, that's just 4. For example, if, I don't know, if this would have been a 6 in here, then you will have here plus or minus 1, a plus or minus 2, a plus or minus 3, a plus or minus 6, and then you will have a bunch of fractions popping up in here. It's just that here the fractions are just over 1. Do you understand this?
Yes.
Okay. So that means if maybe none of these guys are zeros, but if this polynomial is going to have a rational zero, it's in this list. If none of these are zero, that means that the zeros are either irrationals, then you are out of luck. You have to approximate it by using the mean value theorem and so on. I think I discussed this at some point, how to approximate zeros by the bisection method. I remember doing this, so I think I talked about this. You approximate the zeros, and so it's either irrational or complex. Okay, this just give you the rational zeros. Okay, if there are any. Anyway, so from this list, then what you used to do back in precalculus, what do? We have this list. Now you go to a polynomial and start testing one by one to see which one from here is a zero. And the quick way to test is by doing synthetic division. Because when you do synthetic division, the theorem is that the remainder is the value of the polynomial at that point, at that number. So if the remainder is zero, that means you found yourself a zero, right? So that's what we're gonna do, but now we know exactly what's gonna work. We know that one works, okay? So I'm just gonna plug in that. So let me remind you how to do synthetic division. So synthetic.
And you said we use synthetic division if we didn't know one was.
No, we have, but anyway, you need to divide. Now that you know that 1 is a 0, that means x minus 1 is a factor. So to factor this, you need to divide by x minus 1. And synthetic division, you get both. You realize that it's a 0 and you have the factoring right there because you have the division. So
how did you find out that 1 is a 0?
like I said, it's a quick trick. Just add the coefficients. I mean, we're going to figure it out right now with the synthetic division. But basically, you add the coefficients. If you get 0, it means that 1 is a 0. Because what happens when you plug in 1 into a polynomial? You're basically adding the coefficients because all the x's, they become 1. So if you get 0, that means that 1 is a 0. If you don't get 0, then you ignore 1 and then you try something else. Okay? All right, so we're going to do synthetic division. And remember how this is done. So we're going to divide by 1. So I put a 1 here. Then I put the coefficients of my polynomials. Everything has to be here. So that's 1, 0, 3, and negative 4. What is this 0? Where is the 0 coming from? That's the coefficient of the x squared term. Okay? It's not there, but you need to have all the coefficients. If your degree is n, you need to have n plus 1 numbers in here. Okay? Degree is 3, we have 4 numbers. And now we activate the process. So what you would do is, you would do this process with every single number from this list, you would put it here in the red part. And then what you're looking for is at the end to get a 0 here. Because this last number that we're going to get on the line is your remainder. If it's 0, that means the division was exact, so we found ourselves a factor, so we found ourselves a 0. Okay? We know it's going to work here. So what's the process? Bring the first number down, and then what you do is take this number, multiply with the red one, and then put it in the next column. Then you add, you get another number, and repeat until you're done. Okay? So 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 3 plus 1 is 4. 4 times 1 is 4. Negative 4 plus 4, that's 0. So we stop right there. So we realize that because we got 0 here, remember, that's the remainder of the division. So this means that x equal 1 is a 0. So x minus 1 is a factor. Yes? Remember, that's a factor theorem. So x equal 1 is a 0. That means x minus 1 is a factor. So our polynomial, x cubed plus 3x minus 4, can be written as x minus 1 times something. Where is that information?
In the synthetic division.
Very good. So right here. So a synthetic division is twofold. First, it allows you to realize whether you have a 0 or not. And second, when you find it, you already have the factoring right there. Those numbers that you see here, these are the coefficients of your quotient in the division, right? So what's a quotient in the division? X squared plus x plus 4. Good. Questions? Did you understand this? Okay, so now that we have, so we did the first step. Now we need to factor this quadratic. Okay? There are not two numbers to product this 4 and the sum is positive 1, right? So we need to factor this. And let's see, do we have real zeros? Maybe they're complex. So what's the discriminant for this guy? Remember, discriminant is b squared minus 4ac. Okay? So let's compute that, because if this is negative, then the solutions are complex, so we leave it like that. That would be irreducible quadratic. Okay?
What is the discriminant?
Remember the quadratic formula?
Right.
The stuff that goes inside the radical? That's called the discriminant. This expression, b squared minus 4ac. If this is positive, the discriminant tells you the type of solution to expect. If this is a positive number, then you have two real solutions. If this is 0, you have one real solution. And if the discriminant is negative, you're going to have two complex solutions. So here I want to know what solutions I'm going to get, because if they are complex, I know this is prime, and then I don't factor more, right? So this would be 1 minus 4 times 1 times 4. So that's a negative 15. That's less than 0. So that means the polynomial is prime. Because the zeros are complex. Do you understand this? Okay, so now we're ready.
And you said we use it to see if it's prime, if it's.
So a polynomial cannot be factored as a product of linear over the reals, as a product of linears, if the zeros. Every polynomial can be factored as a product of linears, but then the way you factor is by looking for the zeros. The zeros have to be real numbers. If they are complex, then your linear term would be x minus a complex number. That's not what we're looking for. So whenever you have complex zeros, that means that quadratic is going to be prime. You cannot factor over the reals. You need to go into complex if you want to factor. So, and the discriminant tells you whether you're going to have complex solutions or not. So you look for the discriminant. If it's negative, you stop, you say it's prime. If it's positive, you know that there will be two reals, and then you can use quadratic formula to get them. Okay? Just to find those two series and finish the factor. All right, so this as far as we go with the factoring. So now it's time to do the decomposition. So 1 over x cubed plus 3x minus 4 is the same thing as 1 over x minus 1 times x squared plus x plus 4. Okay, so let's do a composition. So this is going to be a over x minus 1. And then the next one, because it's an irreducible quadratic, I need to put a bx plus c. Questions? Do you understand this? Yes? Can I continue? Okay, so now I'm gonna go ahead and clear denominators again. We multiply by the denominator, you know, well, the expression that is under 1, we multiply by this. So on the left, we're gonna get a 1, and on the right, we're gonna get a times x squared plus x plus 4, and then bx plus c times an x minus 1. Here we can use the shortcut to figure out a, right? We can pick x equals 1 to find a, so let's do it. So letting x equal to 1. But actually, you know, the shortcut is not going to work all the time, so I'm just going to go ahead because this is easy enough. I'm going to span everything, okay? Let me span everything. And then this is bx squared minus bx plus cx minus c. That way I need to talk, I can talk less and, and do more. Because the other form is nicer, but then I have to explain a lot of stuff. So then this. So we have a minus b plus c. And then the constant term will be 4a minus c. Questions on what I just did? Are we okay? All right, so now from here we get a bunch of equations, right? We actually get 3 equations. So the first one is a plus b equals 0. The second one is a minus b plus c equals 0. And the last one is 4a minus c equals 1. Yes? Okay, so as I mentioned, it's kind of easy to figure out a. So if you want, we can go back now and find a. It's probably the easiest way if we let x, instead of having to solve this 3 by 3, because once you know a, then we just have a 2 by 2, and we find b and c. If I plug in x equal 1, this is gone, and then we're gonna have here 6a, so a is 1 over 6, right? So note, x is equal to 1, then we get the equation 1 equals 6a, so a is 1 over 6. It's out of the way. So that means immediately now we get b, right? Because notice that this tells me that b is negative a. So b is negative 1 over 6. And the moment that we have a and b, now actually we can figure out c as well. So from here it follows that c equals 4a minus 1. So that will be 4 times 1 over 6 minus 1. So 4 over 6, that's the same thing as 2 over 3. And then this is negative 1 over 3. So c equals negative 1 over 3. Yes? Okay, so once we have a, b, c, now we return and we finish our integral. So the integral of 1 over x cubed plus 3x minus 4 equals, so I'm gonna do my splitting. So a over x minus 1, so our a was 1 over 6, plus, then it was bx plus c, So b is negative 1 over 6 x minus 1 over 3 over x squared plus x plus 4. Okay, this is a good example because we have a lot of stuff going on here. Okay, so now I'm going to solve this integral. How do we solve this? The first one is easy. The first one is ln, right? Now, what's the technique for the next one? So in general, what you can do is, yes, but we need to be a little bit smarter about that. So let me actually just, as I write, because then I say and then I have to write. So, okay, the first one is okay. It's 1 over 6 ln of x minus 1. So that's done. Then I'm going to factor out a negative, okay? I want to have positive stuff. In fact, to make my life easier, I'm going to factor out a negative 1 over 3. If I factor out a negative 1 over 3, no, a negative 6, a negative 1 over 6. That's a smaller one. If I factor out negative 1 over 6, I want you to tell me what will be left in the top.
X minus 2. I'm sorry, X minus 1.
X plus. I'm factoring the negative also.
X plus 6.
X plus 2. Right? 1 over 6 times 2, that's the 1 over 3 that is in here. Okay? I'm just taking out the fraction, that way we have something nicer to work with. And then here we have x squared plus x plus 4. So now we just need to worry about this integral. And what can we do here? Some semesters ago, I gave a test in Cal 2, and I gave an integral similar to this one. And then I put hint. It was not a 2, it was a 3. I put hint. 3 is 2 plus 1. Here I will tell you that the hint is that 2 is 1 plus 1. How can you use that hint? Mind that I give you this integral in the test, and I ask, and then I tell you hint. 2 equals 1 plus 1.
Split the fractions.
And how would that help you?
So you have 3 fractions.
Huh?
You have 3 fractions.
Actually,
you split it so that it's x over x squared, or x plus 1 over x squared plus x plus 4, then you do u sub,
so
and then you do 1 over, and then you do plus 1 over x squared plus x plus 4, which is just ln at the bottom.
we need a 2 here. That's the only thing. So that hint would be helpful if we had the 2 here. But anyways, the idea is exactly that. So I want to have the 2 here. So I'm going to multiply now top and bottom by 2. Okay? So that would be a 4. So I guess my hint would be that 4 is 3 plus 1 instead of 1 plus 1. And the idea is because notice that the derivative of the bottom is 2x plus 1. So if you have a 2x plus 1 on top, that's just an ln. Okay? Do you understand what I'm saying? The derivative of the bottom is 2x plus 1.
Right.
So if we have 2x plus 1 on the top, that's ln. And that way we get rid of this, and then we concentrate on what we need, which is a number over this, and then we will do an arctangent. Because this opens up and this is prime, this is an arctangent integral. And how do we do it? We complete square, like we did at the beginning. This is an arctangent integral. But we need to prepare for that. So, do you understand that the derivative of the bottom is 2x plus 1?
Right.
Yes? So, I'm going to go ahead and multiply top and bottom by 2. So, I multiply the top by 2, and therefore the bottom by 2, but I put the 2 in the bottom outside. Is that okay? So, a 1 over 12 is going to pop up now. Okay? All right. So, then this becomes 1 over 6 ln of x minus 1 minus 1 over 12. Now, my integral is going to be 2x plus 4, but I will strategically write the 4 as a 1 plus 3. Do you understand why I'm writing as a 1 plus 3? Because I want 2x plus, why did I multiply? Let's see, why did I multiply by 2 top and bottom to begin with? What was the...
So the coefficients, the x terms will match. Well, so when you take the derivative, the bottom, you'll have 2x, and then if you multiply with the top by 2, then you'll have 2x there.
Okay, so now you understand why I wrote 1 plus 3. Because I'm looking for the 2x plus 1. right? That's what I want. And now all of this is over x squared plus x plus 4. I'm gonna go ahead and save myself some time and then already split it. Because you know, the next step would be to split it. Yes? The next step would be to split it like this, as two fractions. And why did I do that? Because now the first one is another ln, right? And then the second one is when we do the arctangent business. So now another ln comes from here. So it would be a 1 over 6 ln of x minus 1 minus 1 over 12 ln of, here I don't really need absolute value because this is always positive, right? It's prime and it's a parabola opens up above the x-axis. And now I'm gonna take out the 3, so minus 1 over 4, the 3 cancels with the 12, okay? And now I'm gonna do the integral, the last integral. And to save time, I'm gonna complete the square. So let me complete the square here.
Wouldn't the 3 turn the 12 into a 4 on the first one instead of affecting the second one?
I distributed the 12 with the first one, that is 1 over 12, yes? And then with the last one, we put the 3 out in the last integral. There is a 1 over 12 here, but there's a 3 here. Take out the 3 cancels with the 12, and you get a 4. Yes? Okay.
Oh,
I'm gonna put it, but then I will erase it. It will be like this. Do you understand that?
No, I understand what no, I had confused. I thought the integral was 3 times negative 1 over 12 ln of the bottom. I messed up because I forgot that you turned the bottom into 1 over u.
Exactly.
I messed up, sorry.
Okay. Remember, every time that you have a fraction and the derivative of the bottom is on top, that's ln of the denominator. No need to pass through the u business. Okay, so the 3 cancel with the 12, and that's why there is a 1 over 4, okay? Okay, so now here in the bottom, instead of putting x squared plus x plus 4, what I'm gonna put is the completing square version of it, okay? So I'm gonna complete the square. Let me complete it down here. X squared plus x plus 4. So I need to have here, so 1 divided by 2 squared, so a 1 over 4. So I need a 1 over 4, but then I have to subtract a 1 over 4, okay? So this becomes x plus a half squared plus, what is this? 15 over 4. So that's what we have here. So let me write it like this, as 15 over 4 plus x plus 1/2 squared. And now we are in the context of, you know, completing square. Actually, let's make it easier. I'm gonna distribute the 1 over 4. Why am I gonna do that? Because the 1 over 4 is gonna kill this 4 under the 15. Yes? So we're just gonna have 15. Then I can put the 4 inside the parentheses as a 2 because the square. I'm doing this also to show you algebraic tricks, algebraic manipulations that people do to make their life easy. Okay? The 4 is gonna cancel with this 4. Then when you multiply the next one, comes into a parenthesis as a 2, because when you get into something square, you have to take square root. When you get into something that's square root, you need to square it. Here is what I mean. Let's say that you have square root of something and you multiply by 2. You want to get the 2 inside. What do you need to do? You put it as a 4, right? So you can get it inside, but you have to square it. Does that make sense? I'm trying to do the opposite. Let's say that you have something like this, an x squared and a 2, and want to get these 2 inside. What do I need to do? I square root it, right? Yes? So that's what I'm gonna do with the 4. It's gonna go into as a 2. Why? Because I distribute, I'm gonna kill this 1/2 and becomes a +1. Okay? And I'm just gonna have a nicer expression. Because remember, now you need to factor. If you don't want to do that, then you have to factor out 15 over 4 and deal with all those fractions. I just want to have nice numbers. And I have the opportunity to have them here. So why not? Anyways, keep writing this. And then I'm gonna bring inside the 4 Tell me if you need explanation what I'm about to do, because I don't want to write all the steps, but I will explain if you have questions. The 4 is going to multiply the denominator, right? When you distribute with the first one, what's going to happen? It cancels the 4, giving me a 15. Yes? And plus, now when the 4 multiplies the square, I take it inside as a 2 and distributes over the stuff inside the square. And what do I get? The 2x plus 1. Are we okay? Just do it and then you will see. Okay? Just do it. Instead of asking me, just do it. And then it's going to take you a couple of lines, but then you're going to see it. Okay? Now we activate the process. What's the idea here? But how? What do we do? We factor out 15, right? Because we need a 1 in there. Okay, I'm just going to go ahead and do that integral down here. Because otherwise I have to keep writing all that stuff again. Okay, so now what we do is we factor out 15. So we get 1 plus 2x plus 1 squared over 15. So a 1 over 15 comes out, and then we get 1 plus, I'm going to bring the 15 inside the square. So that will be 2x plus 1 over square root of 15 squared. And now, this is our substitution, right? Now we let u be equals to 2x plus 1 over square root of 15. So du is 2 over square root of 15 dx. So this becomes 1 over 15, the integral of 1 over 1 plus u squared. Okay, dx is 2 du over square root of 15. Of 2 du over square root of 15. No, the other way around. Square root of 15 over 2. So this becomes, okay. All right, I'm gonna leave it rationalized. But typically in this kind of situation, what I like to do is I like to cancel this square root of 15 with this one here, with this 15, and then have a square root of 15 in the bottom. But then, because then the numbers are small, but then it's not rationalized. So I'm gonna keep it rationalized, and therefore I'm gonna have a square root of 15 over 30. And then this is inverse tangent of u. So that would be square root of 15 over 30 inverse tangent of 2x plus 1 over square root of 15. And this result, I'm going to put it in up here, in the tail of this, okay? To finish our problem. So you see, this is the kind of stuff. It turned out to actually be nice because you got to see more complicated scenario than what we have done. But you know, when you make up exercises on the spot, this is the kind of stuff that can happen. But I think it's good. It's a good experience. Minus, and then I'm going to put a result, which was square root of 15 over 30 inverse tangent of 2x plus 1 over square root of 15. Okay, questions? This is basically an exercise like the ones that we did at the beginning of the semester. You need to complete the square and then, you know, add time. All right, questions?
Ask me again while I'm doing the homework.
Say that again? Oh,
ask me if I have questions while I'm doing the homework.
Oh, then, you know, put it on the.
Call me in like 5 hours.
Put it on the forum, and then we exchange ideas.
The problem with the forum is every time I'm almost done posting something, I realize my mistake. So every time I do it,
Well, then that's not a problem. That's
yeah,
good.
it is, but then I feel like I wasted all that time explaining it, but then I haven't
No.
really wasted it because
You didn't waste it because that allowed you to realize
yeah,
what was
it was
going
not a
on.
waste, but it just annoys me.
Drives my girlfriend nuts because I'll like call her over for a question and explaining it, I figure it out, and then she's like, "What? I came over here for nothing."
Oh, that's good. Okay, so I think we got enough exposure to partial fraction. So I'm gonna start with partial fraction at this point. Are you okay with this? Once you start doing the homework, then, but again, remember,
The homework.
there is a question, there is one question in the homework that is very subjective, okay? Which is, what's the hardest step in this problem?
Yeah.
Yeah.
But you know, what did they put in the denominator? What do you have in the denominator in that expression? A degree 5 polynomial.
So it'd be factored.
How do you factor a degree 5 polynomial? You have to go.
Question, Professor.
Well, you have to play all this game with the, you know, the rational series theorem, all the pre-calculus stuff, and even then, you can be there for quite some time. So that's the hardest step. Once you get the factoring, the rest is just tedious, but it's, you know exactly what needs to be done, okay? And here, this is what I just did here. That's the trick. Every time that you have to deal with the, you know, if you get an irreducible quadratic, how do you deal with that integral? Well, that's what you do. Look at the derivative, then make the derivative show up on top. You have to do some little tricks, multiply by something to adjust the coefficient, do a splitting. You're gonna get an ln integral, and then the other one will be a tangent. That's how you deal with that. Just tell me, I mean, I'm not gonna solve it, but just tell me a random polynomial that is irreducible, of course, that is prime. Just tell me a random polynomial to illustrate what I'm trying to tell you. Just tell me a random polynomial, a quadratic polynomial. It has to be prime. Let's make it more interesting. 3x squared let's see. Let's make it bigger because b squared, it needs to be prime. So b squared is a 25. So let's do here plus 20. So when you do the minus 4ac, you know, the negative part is bigger and then you get a negative discriminant. Yes? So this is prime. Let's say you wanted to integrate this. This is already prime. There's no partial fraction to be done here. You cannot factor this. Okay? Let me make sure. B squared is 25 minus 4ac. That's 4 times 3 times 20. That's going to be a negative discriminant. So what I'm saying is, what's the technique? Derivative of the bottom. What's the derivative of the bottom?
6 plus 5, 6x plus 5.
And let's say that I have an x. I mean, if I don't have an x, what I do is I complete the square and I do a tangent. But let's say that you have here, I don't know, x plus 7. And if you want, let's put a 5x plus 7. Okay? Just something in there. Okay, so what I need is a 6x plus 5, not a 5x plus 7. Okay, so let's work for that. I want to have a 6x plus 5 in here. Okay, so all I'm going to do is so I get my 6x plus 5. Yes? Okay, so first I need a 6x. That's the first thing that you need. Unfortunately, I have a 5. So what do? Take out the 5 and put the 6. Professor, why do you do that? Well, I can, because if I put it, and so wait. No. Wait. I'm getting too excited here, and let me be careful. Let me be careful. I'm gonna factor out the 5. Okay, I have to do some preparation, unfortunately. I'm gonna factor out the 5. Okay, now here to save time, what is it that I'm gonna do? I'm gonna put a 6 instead. The 5 goes outside, but then I'm gonna divide by that 6. Yes? Everybody okay? So now when I distribute, I'm gonna have my 6 the place that it should be.
Would you change the 5 inside of the parentheses too?
What do you mean changes the 5?
7 over 5.
Now we're gonna work with that.
Oh, sorry.
Yes? So now I have my 6x. What do I need to have here? 5. A 5. So what's the easy way? Add and subtract a 5. That's what I'm gonna do. I'm gonna do, let me give myself a space. So here I have that 42 over 5. So I need a plus 5, but it was not there, so I have to take it away. Yes? So now you have what you needed. Yeah, I'm doing this because typically you don't see this, but then you get a problem in which you need to do this, and then it's not hard. It's just that if you have never seen it, it's kind of difficult for you to think about this for the first time. So that's why I'm taking the time showing you this. So we get this, and then this was a plus here. This then plus 5/6, and then we need to combine. So -5 plus this, that's 25/5. Negative 25 plus 42, that's 17, negative 17? Yeah. Negative 17, so -17/5 over this guy.
It's not, shouldn't it be positive? Because it'd be negative 25 bits plus 42 bits?
Yeah.
That's to see if you're paying attention.
Uh-huh.
Positive 17. Yeah, 17/5. Good. So, nice. 5 cancel. So now we get here 5/6. Now, what is the first integral?
ln.
That's just ln. You don't even have to think about it. Remember, we did all of this so that we can write this ln, right? Yeah. That's why we did all these steps, so we can write this ln. Okay? Now here, I'm going to put the 17 outside. Now here you do what we did above. Now for this last integral, you complete the square, and then this will be an arctangent, etc., etc. Okay? So I'm not going to continue this. But the point is that, technically once we get to an integral like this, at the bottom is reducible quadratic, we can do it. Because sometimes it's easy, sometimes you have to make all these manipulations to make it work. But we can do it. Remember, the notes are online. Okay. Are you okay with this? Well, you look at it later. All right, so let me have 20 minutes to explain the next idea. The next thing that I'm about to do, okay, there's some stuff going on in the chat.
Oh, that was earlier when we were talking about.
Yes. Okay, so the next thing that I want to show you is, this is not in the book, what I'm about to explain. And it's what you do when you have a rational function, but instead of x and y, instead of x's, you have sine and cosine. Okay? For example, we did a very easy case earlier today, but that one was very easy, that we didn't need it. We didn't need to concern ourselves too much with that. We did this one, right? This is what I mean by a rational function of sine and cosine. If you were to replace everywhere that you see a sine or a cosine, if you were to put an x instead, you get a rational function. Okay? That's what I mean by a rational function of sine and cosine. For example, if everywhere that I see a sine or a cosine, I put an x, let's say a t instead, I will get this in this example. And that's a rational function, right? So this is the type of interest that I want to discuss now. That's what I mean when you see now rational functions of sine and cosine. It's quotation mark rational function, because this is not really a rational function. The top and bottom are not polynomials. But it looks like one if you were to replace sine and cosine by a single variable. Okay? How do we deal with that type of problems? This one, we were able to do it pretty easily. Just make it a little u sub, and then that little u sub turn into a rational function right away, and we solve it, right? But sometimes, for example, what if that cosine was not on top? What if it were just 5? What do? Okay, so that's the type of question that I want to address now. Not sure why this is not in the book, but we do it.
And I suppose we can't just throw in the cosine in the inside of the integral in the numerator and then put one in the denominator to the outside.
You cannot take functions outside. You can only take constants. I mean, you can put the cosine on top, but then you need to put it in the bottom. Inside the integral, you can do your manipulations there, but you can never take a function out of the integral. Constants you can, but not functions. So you get stuck there. So let me tell you what we do in that case. Basically, the idea is that there is a type of substitution that we can make. It's just that we need to work a little bit harder to get that substitution. But once we get it, that will be a theorem. Then you use it. The substitution that you make in that situation, that is guaranteed to always turn that function into a rational function, a fully rational function, and then use partial fraction again. Okay? So when I was tutoring, I learned this substitution. The professor used to call it universal substitution, because basically anything that has sine and cosines, you could use this substitution to transform your integral, and then you solve it. So in a sense, most of the things that we did in the section about trigonometric integrals, with the product of sine and cosine, and then secants and tangent, in special secants and tangents, we can turn into sine and cosines, then do this sub, and then you just do partial fraction. So we could have avoided all of that, then just do this. It's just that sometimes it's easier to use to work with secants and tangents. Anyways, let me get back here. So here is an example of an integral that that we will be interested in solving. I already gave you one before, and here is another one that looks very innocent. But you know, the techniques that we have, they're not gonna help us here. Okay, at this point. So how do we deal with something like this? Okay, so let me explain. We need to take a step back, and I'm gonna tell you a small story of trigonometry. It's gonna be small, it's not gonna be big. So note, hopefully you saw this back in your trig class. If not, you're gonna see it now. I teach it in my trig class, but not sure how everybody teaches it, which is a fun formula for tangent, a half angle formula for tangent. Okay, so typically we have a half angle formula for sine and for cosine. And then for tangent, you know, when people say, oh, it's just sine or cosine. But that formula is going to give you a radical and a plus or minus, and it's ugly. There is actually a very nice formula for half angle for tangent. So note, for any angle theta, what is tangent of theta over 2? So what would be what's a nice formula for this? This is what I want to discuss. And so we don't waste too much time. Let me show you. Let's bring our friend, the unit circle. Okay. Imagine that this is a circle. So it's 1, 1, negative 1, negative 1. And then, you know, let's say theta is here. This works for any angle, okay? It's just that you have to then split it into cases, but it doesn't really matter. So I'm just going to put theta here. But this is going to work for any angle. It's just that you have different configuration. Okay, so given an angle theta, I can always draw it like this, you know, with the vertex at the center in the standard position, and then the terminal side somewhere, and it's going to cross the unit circle at some point. Okay? All right, now I'm going to do the following construction. Here is theta, and now I want to consider this angle over here. Let's see if you remember your high school geometry. What is this blue angle? Theta is called, let's see if this rings any bell. Theta is called central angle. The blue angle is the angle inscribed on the same arc as theta. There's a theorem associated to this angle. No. There is a theorem that you learned back in high school geometry about this angle. So this angle is going to be half of its corresponding central angle. Okay, so this is called an inscribed angle. Why? Because it shares the same arc as the corresponding central angle, theta. They share the same arc, and then, but this one is more than theta. It's actually half of it. A particular case of this is Thales' theorem. What does Thales' theorem says? When if you have a circle, the angle that's inscribed on the diameter, so the corresponding arc is half a circle. What type of triangle is this? This is a right triangle. This angle is 90 degrees. That's called Thales' theorem. Okay? And it's actually a particular case of this, because this angle is half of the corresponding central angle. What's the corresponding central angle? Pi, or 180. So this one has to be half, so it's 90. But this works in general. It doesn't have to work only for this situation. Okay? Anyways, this guy here is theta over 2. Okay? All right. Now, what are the coordinates of this point? This is the unit circle, so the coordinates of this point are cosine of theta, comma, sine of theta, right? Cosine, comma, sine. The x is cosine, the y is sine. I'm going to drop a perpendicular here. So we have a right triangle here. Yes? Okay. How much is this piece? That's equal to 1 because that's just the radius of the circle. How much is this little piece? That's cosine because that's the x of that point. I just projected a perpendicular down. Yes? And how much is this? That's just sine. Okay, so what do we want? We want tangent of theta over 2. Look at the triangle. The yellow triangle. What's tangent? Opposite or adjacent? What's the opposite? Sine. What's adjacent? 1 plus cosine. So this is a beautiful identity. And it's going to help us solve some interesting intervals like the one above. Okay? All right, so that's the trigonometry. Now, let's go back here. I'm going to do some algebra now. Okay? I'm going to do some algebra now with this. Any questions before I move on? No? Okay, so the substitution that I want to do is u equals tangent of theta over 2. Okay? So how would that help us? Well, let's see. So let u be equal to tangent of theta over 2. Then what I want is to write sine and cosine. Because remember, we're dealing with functions that have sines and cosines. I want to write sine and cosines in terms of u. This is what I'm about to do now. Is so that I write sine and cosine in terms of u. Okay, that's my goal. So if I let u equals tangent of theta over 2, of course, that's like saying that u equals sine over 1 plus cosine, because that's what tangent of theta over 2 equals to. It's going to be clear in a second why I'm letting u equals this, okay? Let's just go with this for now. All right, so my job now is to write sine and cosine in terms of u. So here is a trick that I'm going to do. I'm going to square both sides. Okay, so from here it follows that u squared equals sine squared over 1 plus cosine squared. Why did I do that? Because now sine squared becomes 1 minus cosine squared. So I'm going to go after the cosine first. Now I don't have sine in the mix. I only have cosine, so I can do something here. In the top, that's the difference of squares. And luckily enough, we have a factor in the top that cancels with one of the factors in the bottom. So this 1 plus cosine cancels with one of the 1 plus cosines that we have in the bottom. All right, so we have the u squared equals 1 minus cosine over 1 plus cosine. Now we are in business. We can solve for cosine now. So we get the u squared times 1 plus cosine equals 1 minus cosine, distribute. Bring cosines to the left, whatever doesn't have cosine to the right. Factor out cosine. Divide. So we get that cosine is 1 minus u squared over 1 plus u squared. So if I let u equals tangent of theta over 2, then I have a substitution for cosine of theta, which is 1 minus u squared over 1 plus u squared. Okay? You can look at the algebra later, all right? But let's just continue with this. All right, so now let's figure out sine. So again, I'm after sine now, but now it's easier because we have that u, remember, was equal to sine over 1 plus cosine, which means that sine is u times 1 plus cosine. But now I know what cosine is, so I'm going to put it, right? So I know what cosine is. I'm going to put it in here. So that becomes u times 1 plus 1 minus u squared over 1 plus u squared. So combining this, I'm gonna get 1 plus u squared plus 1 minus u squared. I'm just adding these two. The u squares are gone, and we have a 2 on top. Distribute the u, so we get the sine is 2u over 1 plus u squared. So my cosine was written in terms of u, my sine is written in terms of u. Okay? All right, so we have this. Now, why is this helpful? Let me put this into context now. Let me bring back our original variable, which is x. Now, instead of theta, I'm going to move to x, okay? These are identities so far, what we have, okay? So now, switch to x. If we let u be tangent of x over 2, right? Because typically that's the variables that you have, x, like sine of x, cosine of x in your integral, okay? We make this substitution, u equals tangent of x over 2. Here is the good thing about this. First of all, by the argument above, that means that sine of x is going to be 2u over 1 plus u squared. Cosine of x is going to be 1 minus x squared, 1 minus u squared over 1 plus u squared. And if you think about substitution, the only thing that we need to do is we need to say something about dx, right? Remember, when you're making substitution, we are dealing with a function that only has sines and cosines. So here we have a substitution for the sine, a substitution for the cosine. We just need to do something about the dx. That's where this comes into play. From here, this means that x over 2 is inverse tangent of u, right? So x is 2 times inverse tangent. So dx is 2 times, what's the derivative of inverse tangent? It's a rational expression, du. So basically dx is 2 over 1 plus u squared du. This right here allows to turn any integral that has a rational function with sine and cosine. So any integral of a rational function, sine and cosine, quotation mark, because it's not a rational function, just turn into an actual rational function. Every place that you see a sine, you put 2u over 1 plus u squared. Every place that you see a cosine, you put this expression. And dx is this expression. After you simplify everything, you're going to get a rational function. Then do partial fraction. Okay? So that's 5 minutes, so let me illustrate this with the above example. So theorem, this substitution turns any integral, okay, with this substitution turns any, I would say any integral of a rational function of sine and cosine into a rational function of u. Okay? And once you have a rational function of u, we have a lot of techniques to deal with this. Okay? So let me show you the example. So for example, let's do the integral of 1 over 3 minus 2 cosine. Okay, so substitution is u equals tangent of x over 2. And therefore, once we declare that this is our u, then this immediately comes with these 3 formulas that we derived. Okay, so we have the sine. It doesn't really, I'm just going to write it, but we don't need it here because there is no sign, but just going to put it. Okay, then we have the cosine. So we already did the derivation 1. We don't need to do it again. And then we have the dx. That's a theorem now. So you go to your integral, and then you replace this. So it'll be 1 over 3 minus 2 times, okay, cosine. That's a 1 minus u squared over 1 plus u squared. And then the dx is 2 over 1 plus u squared du. Now let's simplify and see what we get. I'm gonna distribute this 1 plus u squared, okay? So I'm gonna get a 2 on top, and then when I distribute, I get 3 times 1 plus u squared minus 2 times, and then this 1 plus u squared cancels this one down here. So I get 1 minus u squared. Okay, let me leave the 2 in there. So distribute the 3, so 3 plus 3u squared minus 2 plus 2u squared. Combining like terms, we get 2 over 1 plus 5u squared. And this is an easy arctangent integral, right? So this would be 2, 1 over 1 plus square root of 5u squared. So if I let t equals square root of 5u, then dt is square root of 5 du. So du is dt over square root of 5. So this is going to be 2 the integral of 1 over 1 plus t squared dt over square root of 5. So this integral becomes 2 over square root of 5 inverse tangent of t, which is then 2 over square root of 5 inverse tangent of the square root of 5 of u. And what was u? Tangent of x over 2. So this becomes 2 over square root of 5 inverse tangent of the square root of 5 times tangent of x over 2. Okay? Again, the whole point is that with this substitution, you will get a rational function, and you may or may not need to do partial fraction. Here we didn't need to do partial fraction. We were lucky enough that we got something nice that it was a tangent right away. But you know, here we could have gotten something that then you need to factor and do partial fraction, etc. That's how it will be in general. Okay, so again, I just wanted to have this here for completeness. This is for you. Like I said, it's not in the book, but it's a very useful theory. Okay, so it's good to know.
Are we going to continue this next class?